Let's do Rydberg. Okay. Oh, yeah.
We're going to ask a question about, I guess, pressure flow, or more so either like to a mole fraction, like kind of an example or a second order expectation
Can you stick around so I do specific questions on one of those? Will you remind me? Okay. We'll do another Dalton's Law later after I get to the general topics. Okay. If I ask you an orbit question, meaning let's say I say you have an electron on the 4th orbit and it falls down to the 2nd orbit and I want to know the energy. Okay, what's the energy of this occurring here? Or sometimes I might say the change in energy. If I ask you with the orbits, the only equation that you have is what I'm calling the Rydberg equation, which is this one. Rydberg constant 1 over the n initial squared minus the final orbit squared. And then you just plug and chug. The Rydberg constant will be given on the back of the exam. 2.179 times 10 to the minus 18 joules. Times 1 over the n initial, 4 squared, minus 1 over n final, 2 squared. It'd be nice if I knew this number, but I don't really do this. If somebody wants to calculate that for me, that'd be awesome. But while I ask the rest of you, is that a positive or a negative number for an answer? Well, mathematically, what would I get? A positive or a negative answer? Negative. What does negative mean? Negative means released. That's all it means. Energy is given off. That's it. So, will I carry this negative number into future calculations? No. Just make it a positive by taking the absolute value. Okay. Can somebody calculate this for me? Oh, that's not helpful. Okay. Okay. All right. That's cool. An additional question I could ask you that I could likely ask you on this is what's the wavelength? Or I could ask you what's the frequency. In that case, remember that E equals h nu, that will be given on the exam, and hc over lambda. So if I wanted nu, it's just energy over h. If I wanted lambda, it's hc over the energy. Okay, so you could use equations like that. So it's common, I might not ask you for the energy, but I might ask you for lambda. So know that it's just a combination of formulas, that's it. One thing I could also ask you is what's the electromagnetic region that goes with that? In that case, you'd have to find nu or lambda, so frequency or wavelength. And then you need to look on an electromagnetic spectrum to see what the energy would be. We did one of these when we first did this equation. I don't know if you remember, it was a week or so ago, and that one had the answer of the IR region. So if you want to look back and see an example like that, you'll also see it on the exam. Okay, yes?
I have a calculation, but other than that, how would you find your final n for this problem?
How do I find the n final?
Yeah.
It was given to me.
No, I mean, if the question asks what is n final, you can use the equation.
Okay, so if it asks what's n final, giving you the equation, there's a couple things to think about. First of all, the good news, this is just plug and chug. So it's just this formula. So if I was asked for n final, I'd have to give you the energy, and you'd have to know n initial. Is that okay? You just plug and chug? But there could be a conceptual question I could ask you. Let's say I said the electron was ionized. And let's say I gave you all kinds of information. The energy for the ionization, I gave you the Rydberg constant, I gave you the initial orbit, and I asked you what's n final. What would you say? What would you do? How do you find n final if I ionize something? Okay, good, I asked. Oh, yes?
So
That's right. You got it. If I have an electron, wherever it is, okay, this would be like a conceptual question. And I ionized it, it means I remove it. To remove it, this is going, N final is going, approaching infinity. So it's near pretty much infinite or approaching infinity. So if there's anything about ionization, N final is infinity. All right, let's move on. Let's do some quantum number stuff. For quantum numbers, did you want to just see some examples? Is that helpful? Yes? Okay, let's do some examples then for quantum numbers. There's several types of examples. Let me see if I can remember all of them. One type of example, let's say I give you n equals 4. And I ask you, tell me the number of spin down electrons. What's the number of spin down electrons? Okay, how do you do this kind of problem? If I say spin down electrons, what quantum number am I talking about? Ms. So somebody who asked me for Ms, there's two values, spin up and spin down. They're not in any way mathematically related to the other three. The other three are mathematically connected, but not the spin quantum number. So what you would do to get there is you have to go through the other ones. So what you would do is say, okay, what could L be? Well, L could be, what's the highest that L could be? 3, what's the smallest it could be? 0. There's L. Next, you'd want to go through what's M sub L. And I'd recommend writing it all separately. You're going to get some duplicate numbers. That's okay. All right. M sub L could be, 0 plus or minus 1, plus or minus 2, plus or minus 3. So it's between positive L and negative L, between plus 3 and minus 3. For the next one, it's between plus 2 and minus 2. For the next one is between plus 1 and minus 1. And then the last one is between plus 0 and minus 0, which is just 0. Any questions on how I got the M sub L values? Yeah?
I have a question about the last section. Do we have to know the visible light spectrum?
That's right. In the last question about the electromagnetic spectrum, there's one part you need to know, and that's the endpoints of the visible light spectrum. So since you asked that, red, anybody, is approximately what wavelength? Around 700. Blue is around 400. If it's something else besides that, I'd have to actually give you the spectrum. But if I happen to give you something that's one of those numbers or close to it, you don't need it. Okay? Good. Great, great. Okay. Each one of these represent what? Each one of these values here represents what? These are orbitals. Each orbital can hold how many electrons? 2. So that means this one can hold 2. This one can hold 6. Is that cool? Because there's 3 of them. This one there's 5, so it can hold 10. This one there's 7 digits there, so it can hold 14. Okay, the total number of electrons this could hold is 2032. Is that right? Did I count that up right? Yeah. Okay, so the total number of electrons that can be held in this n equals 4 orbit is 32. How many of those are spin down? Yeah, half of them. Half are spin up, half are spin down. So 16 spin down. Okay, turn to a neighbor, make sure your dopey neighbor actually gets this. I know it's not you, it's probably your neighbor. yes, I counted the number of orbitals under M sub L. How did I get the column on the very right? Because it went up to 0 to plus minus 3, that's a total of 7. Each orbital holds 2 electrons. That's 7 times 2. Is that okay? Yeah. So you need to know each orbital holds 2, one to spin up, one to spin down. Yep. Is L associated with the number of nodes? Not necessarily, because it's kind. I see where you get that, but let me ask everybody: how many nodes would I have had in this orbital? 3 at minus 1, but L could be 2 or 1 or 0. So the number of nodes is equal, I guess, to the maximum L value, but not any possible L value. Yeah. Okay, here's another sort of question, fill in the blank. So, M sub S, I told you that one's not mathematically connected, right? So it doesn't matter what's over here, if you, and I'll do this in a different color for the answer. It doesn't matter what's anywhere over here, this always has to be plus or minus half, if I don't give you any other information. Okay, if M sub L is minus 1, what is the smallest value L could be? So let's just make sure, can L be 0? Okay, I know in general in life L can be 0. I mean in this problem, can L be 0? Not in this problem. Because if L was 0, I can't get a minus 1 value from it. Is that okay? Because M sub L is between minus L and plus L, that wouldn't work for 0. So L could not be 0. Alright, can L be anything else besides 1? What else? 2, 3, 4, ... Any of those numbers could give you a negative 1 for the M sub L. Okay, given this information on this page, what's the smallest N could be? 2. Do you see that? Because if the smallest L could be was 1, then the smallest N could be is 2. Because it always has to be 1 bigger. But because L can be bigger, so can N. Okay, let's do another time. Let's look at lithium. Let me write out its electron configuration in this form. Lithium would be 1s2, 2s1. And let's say I'm really interested in this electron right there. Okay? That one right where the brown arrow is. I want all 4 quantum numbers for that electron right there. Okay? I'll give you a 10-second head start on me. See if you can get it. All 4 quantum numbers for that one right there. What's N? 2. How do you know that? It's a 2s. 2 is the N value. What's L? 0. How do you know that? Because S means 0. What's M sub L? 0. How did you know that M sub L is 0? Because L was 0. If L was 0, then M sub S has to be 0. So far we've got a 2, a 0, a 0. What's M sub S? Yeah, now this is particular. It's plus 1/2 because it's pointed up. So it's an up spin. Okay, any questions on this? One more of these. Can I just pick another electron? Okay. This one. Is that cool? Okay, I'll give you 5 seconds. As soon as I can write this down, that's all you get. That electron on the right in the 1s spot. Okay, N is 1 because it's a 1s. L is 0 because of the S. M sub L? 0 because L is 0. And M sub S? Negative 1/2 because it's pointing down. Okay? All right, that's quantum numbers. Let's do electron configuration for some transition metals. Electron configurations for transition metals. Let's do a warm-up first. Technetium, TC. I'm going to write a couple down if you want to get a head start on me, but I'm going to do these for you right now. Okay, that's only the easy one. Then we'll get hard. Oh, yeah. Okay. We got a head start. Okay. TC. Number 43. So you got a previous noble gas, which is krypton. Krypton number 36. The next level is what? 5s2. And then 4d, how many? 5. Done. That was nothing special about that. Anybody know the name of this right there? Tell me right now before looking on your phone. Okay. It's not uranium. Uranium is number 92. This is unium. Unium. The next one is bium. And there's straight. So the means 1. So 112, you're digging the numbers. Okay, unium is radon. Number 86 is the previous noble gas. And what do I write next? 7s2, that's the 7th row of the s's. And now notice, I'm going to go through the f's. So let's just do the f's next. It's what level of f? 5f. 14, because I go all the way through them. And then what level of D's? 6. Now you're going to know something funny is going to happen. What do I get here? 9. If you count over, I'll get 9, but that's not correct. Why is this not correct? Yeah, remember there's an exception. Anytime I'm in the 4th column or the 9th column periodic table. Right now I'm in the 9th of the transition metals. So copper, silver, gold, and unium does not fill like this. It fills a 1 here and a 10 there. That happens every time on the 4th column and the 9th column with the transition metals. You half fill the S, and you put the leftover of the S's in the D's. Okay? Any questions on that one? Okay? Moly. Molybdenum. Number 42, the previous noble gas is krypton. Now what do I write here? I just said, right? The 4th and the 9th column, this is the 4th column. Is that cool? Good, we did 2 of them. Okay, now for moly plus 1. Which electrons do I remove now? Yeah, that S. Remember, the S's go before the D's for a transition metal. The S's go before the D's. So if I have to remove another one, now what goes? Now the D's go, because there's no S's left. I remove another one, again, there's no S's, so I have to remove a D. Okay? Any questions on those? I think that's plenty of examples. Yes?
Are we ever going to be given like a formula like KR43 and supposed to find out that
Oh yeah, would I have to go backwards? For sure. Of course. How do you do that? Okay, that's why you asked probably. You look at krypton. Which one do you want to do? Backwards. The 3 plus this one. You find krypton on the periodic table and you write down its numbers, 36. Then you realize every superscript represents an electron. So see all the superscripts here? Those represents electrons. So you add 3 to that number. This will give you the neutral element. So the neutral element will be number 39. So that's yttrium, Y, right there, yttrium. So you can find out the neutral. If it was an ion, I have to give you an additional information. So for example, I'd have to tell you, in this case, it's a 3 plus ion. Find it. Well, you count over 3 more, and it's moly 3 plus. If I said it's neutral, then it's yttrium number 39. Okay? Yeah, yes?
Could you do the electron box diagram for the TP?
Yes, I can do that. I'm just thinking, would I ask you that question? Yeah, that's doable. That is doable. I wouldn't ask you that for like this one. Do you want vertical or horizontal?
Horizontal.
Horizontal. So then the krypton, you just ignore that part. And then you go put a box for every one. So for 2, 3, 5. We've got the 5s and the 4d. Okay? For the 5s, there's 1 electron there. Oh wait, am I doing the right one? I was looking at Molly. Sorry. 5s, there's 2 of them. Oh gosh. You see all this? Let's see now. There we go. For the 5s, it's 2 actually. I was looking at Molly. 5s 2. So we go like that. And for the D, there's 5. Here's how you fill them up if you don't know. 1, 2, 3, 4, 5. Number 6 would be paired, and the rest would be paired, so on. Okay. Is that cool? All right, let's move on. Did that. I haven't done those yet. Okay. How are we doing? Okay, I have a couple more minutes. Let's do the wave functions next. For the wave functions, what did you want me to do? Did you want me to overview? Do you want me to draw them? Do you want me to help you find nodes? What would be helpful? Nodes? Okay, I can do that. Is that it? Do you want me examples of drawing them? Okay, is that good? So nodes and drawing. All right. So let's say a question I've had on 3 or 4 exams was draw all the 3d orbitals, all, and label the axis and label all nodes. So let's just start there. That's a good place to start. And you have to write, which orbital you're drawing. So the dxy would be on the xy axis. It'll look like this. The dyz would be almost identical. It's just you change the axes. I'll draw the nodes at the very end. There's the dyz on the yz axis, and then the dxz looks almost identical to those two. It's on the xz axis though. It looks like that. The ones that look different are the next two, the dx squared minus y squared. This is on the xy axis. And then the dz squared. This is on the z-axis. There's the 5d orbitals. I'd also have you label the nodes. So you would go something like this. For the first one, node here, here. node, same thing, here and here, node, here and here. And then for this one, the nodes are off axis. There, there, node. And I wouldn't care what the heck you did here. Just give me credit for it. But the nodes would be like this, if you wanted to draw it. We wouldn't grade you on this one. Okay. So there's an example of drawing all the 3D orbitals. That has been on many exams in the past. I could have you, do you want me to draw, now I'll draw, oh, these all have 2 nodes. And I knew that because I take the number of nodes is n minus 1, and it's 3 minus 1. All of these are what type of node? Angular. So you could say a d orbital always has a minimum of 2 nodes, and though it's born with 2 nodes and they're always angular. Okay. A p orbital has a minimum of how many nodes? P orbital, 1. It's also what kind of node? Angular. An f orbital then would have a minimum of how many nodes? 1 more than this one. 3. Because 4f is the lowest energy f orbital, and so 4 minus 1 would be 3 nodes. The s orbital, if it has a node, is what kind of node? The s orbital. A radial node. Can an s orbital have an angular node? No. An s orbital can only have a radial node because an s orbital is not born with any planes in it. So if I wanted to draw a 3s orbital, for example, that would have 2 nodes, and they're both radial. One's there, one's there. These are both radial nodes. Okay? All right. Did you want me to do any other examples? Okay. No? All right. I think I'll have time for one more. I'll quickly do a Heisenberg uncertainty principle. This is the equation I'll give you on the exam, but this isn't practically what you would use. You would change this to look like this. X times P is mass times velocity. And then the deltas are represented by some uncertainty given by a percentage. And then just change it to an equal sign to make your life easier. Okay? Is there any locked out anybody on that? Same as what we did in class. We've got P is M times U. There's always a percentage in the formula equals H over 4 pi. So this kind of question is a plug and chug. How do you know it's this sort of question? You're probably going to see the word Heisenberg, and or the word uncertainty, or the word accuracy, or the word precision, or a combination thereof. That's how you know it's this sort of problem, and you'll have all of these variables. So it would say, what's the uncertainty in the position X for an electron going 1/10 the speed of light. The velocity is known to a 2% accuracy. Okay, so it's one of these problems. You see the word uncertainty. I didn't write it, but there's a word precision or accuracy here as well. So you want to know X. So in this case, you solve for X. That's the position. X equals H over 4 pi M times U times the percentage. So X, and really it's delta X you're solving for, but they're just making it a little simpler. H is given on the back of the exam, 6.26 times 10 to the minus 34 joule seconds. 4 is 4. Pi is in your calculator. M is the mass, in this case, of an electron. It's given on the back of the exam, 9.109 times 10 to the minus 31 kilograms. U is 1/10 the speed of light. Speed of light is given on the back of the exam, 2.9979 times 10 to the 8th meters per second. And then the percentage, make sure you put in fraction form for calculation, is 0.02. By the way, how many sig figs will I have in my answer? Typically in this sort of question 1, and you can see it with a percentage, only have 1%. It's pretty normal, this sort of question only have 1, maybe 2 sig figs. Okay, whatever that is. Okay, I'll let you calculate at home. Should I work out the units for you since you asked me about that earlier? Let's do the units just so you can see how this works. It'd be a joule second. 4 doesn't have units, pi doesn't have units, there's kilograms, and then a meters per second. Okay, so that's a joule. The second flips up, second squared, kilograms times meters. So you need to know what a joule is. A joule is a Newton meter. Times a second squared still, kilograms times meters. So there goes your meter term. That's gone. Next, I've got to write out whatever the heck a Newton is. So let's do that. A Newton is a kilogram meter per second squared. I've still got the second squared. I've still got the kilograms on the bottom. Notice that the second squared drop out and the kilograms drop out. I'm left with a meter. Now I should think, does that make sense? Yes. The only possible unit, even if you didn't know any of this, was meters. Okay? All right. I'm going to pause now. Those of you who want to go,